All right, we're continuing on this. I hope I still got the ink tools. There they are. In other words, R cross F really is the most descriptive. A lot of people put theta sub F minus theta sub R, but realistically that's a two-dimensional direction. So really you're better off giving it a deflection angle between. So in other words, a better answer, if you would, we're not going to use R cross F, is the magnitude of the force times the magnitude of the radial vector. I guess these should be switched around, doesn't make a difference, times the sine of the deflection angle. Because that will give you the magnitude. Of course, that doesn't give you direction. This gives you direction. Number 18, that's what that one was. Number 19, the definition of weight. Weight equals mass times the acceleration due to gravity. Hopefully on this planet, maybe not in our careers, just on this planet. What formula is used to select a member in tension to a stress criteria? Well, basically you want the stress axial to be less than or equal to 60% of yield stress, and you can actually go a little bit better than that. You could go P over A is less than or equal to 60%. And in this case, you get the full amount because it is tension. You realize you can kind of use that. You don't want to go much beyond that, 60%. In other words, if you have a stress-strain curve here, and that's the yield point, you're someplace in the 60% range. You're still within a point where you're not going to get into kind of fatiguing when you get up above there. 21, what formula is used to select bending? M over S is less than or equal to 60% of yield stress. And that, again, changed. This number can actually go up a little bit if everything is cross-braced and everything else, and it can go down a little bit if you don't have lateral bracing. What formula expresses internal reactive moment as a function of shear? Kind of like we saw before, it's a function of shear, so we're looking something like this. The moment at x is equal to the initial moment plus the area under the shear curve from 0 to x. I didn't use an integration here, but it's a function of shear. And you'll see that really is a way that you can skip some of the kind of matrix algebra we've done in terms of walking what's behind you just by doing some mathematical graphics on a simply supported beam, for instance here, if that's a pin joint and that's a roller joint and that's simply supported with W, the shear diagram looks like this. And if you want to know the moment at any point, you take the area to the left, which means this looks like the moment curve looks like that. It's parabola. The slope of the moment curve is equal to the value of the shear curve. Therefore, the slope there is at 0, just like in your vertical curves. Number 23, what formula can we use to calculate the moment of inertia? One knows the radius of curvature in the area. Basically, R equals the square root of IA. You would have been looking for a formula that has 3 of these, and this was the only one. Basically, if you square it, you get I equals R squared A. And that's actually one of the places you'd see a definition, depending where you're looking around. The moment of inertia. Moment of inertia, really it's the second moment of the area or the fake one. Oh, losing my pages here. I'm going to keep going here. Hopefully we'll get down and through in these last 10 minutes. What formula is the one you should know to calculate the moment of inertia for a rectangle about its centroid? Be careful, not about its edge, but its centroid. I about the the xx axis of the centroid is equal to bh cubed over 12. In other words, if you have a rectangle here and you want to rotate it about its centroid there, you take the height and the base and you cube the height and multiply by the base. We've done that a lot with a 6 by 6. You really should have done it at some point with a 1/8 by 1/8, which would be 1/64 for an area. And you'd think even less when it came to a moment of inertia. So, 25. What formula describes this definition of section modulus? S equals the moment of inertia divided by the half depth of the beam. And this is what you use as often as anything else. It includes 2 of the aspects of the geometry of the beam, something that describes the shape and something that describes the depth. What formula describes the definition of mass density? I'm kind of amazed at how many people grab that one. Rho equals mass over volume. Gamma equals rho times G, or rho times G, which is mass times g over volume, which is weight over volume. I asked for the mass density. What formula expresses the energy stored in a spinning flywheel? This one comes kind of from that discussion, Professor Lewin. Energy is spinning in a flywheel. You may not think of it as being stored, but it can be pulled out and put into a magnetic field or into a car, for that matter. And so the energy of rotation is kinetic energy equals 1/2 I omega squared, where omega is its angular velocity in radians per second. Radians per second, of course, are not, radians have no units. 28, when formula expresses in a variable way the allowable stress in the compression member. That, of course, was F axial, or in compression, should be less than or equal to some K times the yield strength. And, of course, that big K is a function of the slenderness ratio, KL over R, with that being the constraints on the ends, that being the unbraced length, and that being the radius of gyration along the weakest direction. If you look up in W shapes, basically something is going to have a moment of inertia about its XX axis and its YY. So it's going to have a radius of gyration about the XX and a radius of gyration about the YY. Many of these will be equally resistant to rotation or spin about either axis, but many others are not. They're going to be more resistant along the strong axis. You have to be aware of that when you are bracing structures. Number 29, what formula expresses the definition of the second moment of the area about the XX centroidal axis? Basically, if you're thinking about it without calculus, it's the sum of the area, distance squared times the area. With calculus, it's the integral of y squared dA from 0 to all the a's, from 0 to a. So you're going to go ahead and you're going to basically 0 to x, basically dx, I think is probably how that turns out. All right, so that is one that I was looking for, the integral of y squared dA. I will let you know that one might actually have it wrong, so I have to check what I put in there. But basically, you're looking at the second moment of the area. Number 30, what formula is used to calculate the average shear stress across a face? V is shear, A is area. It's across the face, so this is the shear stress. It's usually F sub V. What formula or expression forms the denominator of the pressure head equation? You have to, and again, maybe it's unfair to repeat something over and over again, but Y is the pressure head, elevation head, plus the pressure head, plus the velocity head, plus any head of the pump equals, at some other point along a flow line, the second Y, plus the second pressure over gamma, plus the second velocity over 2g, depending if you got what's going on, plus some head loss, and head loss is proportional to velocity head. And so what formula expression forms the denominator of the pressure head? Gamma, unit weight. Moving on. 31. What formula calculates the energy of a spinning pool ball with enough backspin English so that it makes, so as to make it reverse its direction along the felt? So it's spinning along here, it's doing a backspin, it stops translating, it's still spinning, it's got kinetic energy equal to 1/2 I omega squared. So this rotational energy, in essence, is in these equations because we start with torque, we start with 1 over rho equals the amount of spin external over the resistance to spin, and then all of a sudden when this breaks, you get torque equals I alpha. That I alpha makes omega, or angular velocity, increase, and eventually you have a whole bunch of energy, 1/2 I omega squared. All right. Finally, and we'll be done then within the 10 to 20 minutes there. Finally, what formula is the equivalent of a change in momentum over change in time? This one, I don't mean to be overboard about it, but really understanding that force is the change in momentum over the change in time, and if the mass stays the same, it's actually the mass times the change in velocity over the change in time, and the limit as change in time goes to 0 is the acceleration. Force equals mass times acceleration. And so this is the answer, and it's probably one of the more important ones. All right, going back through this, they're all laid out. You should come up with some sort of small little, you should write out these equations on a sheet, and some with some small way you're going to remember, at least if not the equation, the concept to which these are tied. Thanks for listening.